Okay. So I have practice problems, but we don't have to start with those. Yeah, it is. That's what I was doing up here. That's why I'm a little late starting. But if you would rather go over questions from like homeworks or last exam, we can do that to start and then do practice questions. So what questions are there? Yeah. Yes, let me pull up for third homework. Actually, I'm gonna say our time is better spent covering a different topic. Other questions? Yeah.
On homework 3, question 5, I wanted to ask specifically, how do you know which, like, you said in, you said 3 verses, how do you use that?
N is the only one that has a lone pair. You could also technically, well, you can't really start with the oxygen because there's not really anywhere to go. But N has a lone pair. And resonance structures, the whole gist of resonance structures is it moving electrons. So you have to have some kind of electron to start with. Other questions? Yeah. We'll do a practice question about NMR. Other questions? Yeah. Yes, so we will. We'll walk through a practice problem. Yeah. I can't answer, like on the exam, I can't answer like a straight up question like that. But I have some practice questions about identifying reaction types. No? Nothing else? Yeah?
Also, when it asks you to do an electric coefficient, I don't understand why. Like, I understand you're adding a hydrogen, but doesn't really also have a negative?
So it has a negative, which means it's a nucleophile, not an electrophile.
But that's the example you gave, I guess.
Yes, but so which question is this? Number 1. Yes. So you're adding the H plus, like the electrophile first. Because HBr is a strong acid, so it exists in its ionized forms where it's H plus and Br minus. And so your first, oh my God. Your first, that one is too skinny. So you have H plus and Br minus. This is going to attack here. And you'll have an H and a new cation. And then Br minus can add here. Would we prefer to just get into the practice problems? Okay. So the first one is SN1, using SN1 to create these products. So this question uses both resonance and a mechanism. So it's kind of building on the concepts we know. Did the upload of these questions go through on Canvas for those of you? Okay. iPaders. Yes. So where do I start with this one? Anybody have any thoughts? With the bromine? Yeah. So the first thing you'll see is the loss of your leaving group. Oh, that's not right. So now we have a cation that is perfectly primed for connection with our nucleophile. Yeah. Yeah. That's okay. Testing. Hello. Better? Okay. So SN1 is our stepwise reaction. We also have E1. Those are our stepwise eliminations. But this is a stepwise substitution with nucleophiles. So we've just kicked off our first nucleophile, and now we're like primed for our next nucleophile to substitute in. But we have resonance structures here. How can I make a resonance structure? What can I move around on this molecule? The double bonds. So I can do just one shift. And I get a different cation. I can do another shift. And get another cation. So that gives me 3 different starting materials. What is my next step? Yeah, so now our sulfur can add. And that gives us structure number 4. That gives us structure number 5. And this gives us structure number 3. So when you're doing a mechanism, that is when you do the curly arrow thing. What about disconnection analysis? What would I need to do differently to show this reaction using disconnection analysis method? What's the first step for disconnection analysis? Disconnect. Our only disconnection is the loss of our bromine. Then I can indicate what new bonds are formed. What is the type of bond I'm looking for? What two atoms will participate, or elements? The sulfur. So we're looking for a carbon-sulfur bond. And then what intermediates would I need to draw? For the star things, what would I need to draw? Yeah, so the stars replace the charges. So I can do the R star, and then I can draw all my resonance forms with stars. Do I need anything else? Yes, no, maybe so. Yeah.
How do you keep up with the positive and negative in this section? I feel like that's where I get confused once it starts.
You don't. That's like kind of the point of the stars is that they are stand-ins for ambiguous charges.
Okay. So resonance pose.
Yeah. I would say when you're doing resonance structures, do your curly arrow method first and then your disconnection analysis. Usually we see on exams and homeworks that he asks for both disconnection and curly arrow. And there's obviously no penalty for doing question 2 before question 1. So I would say if disconnection doesn't make the most sense to you, do your curly arrow first, and then anywhere that you had charges, you can draw in the stars. Yeah.
So like I know on the homework that is due tonight, that there's a portion that has a lot of quiz instructions. Do you have something like that needs to go into a sample more than 3 or 4 different questions?
You have a time limit on exams, and he knows that when writing them. So that kind of question is really good for homework where you kind of have not unlimited time, but a lot more time to work through all the resonance structures. But on an exam, a question like that would eat up a lot of time just drawing out the structures. So no. Yeah.
Resonance in itself. I don't really know where to start.
Yeah. So with resonance, we always want to start with some kind of source of electrons. So like our rules with resonance are we never want to break the like true connectivity of a molecule. Can anyone tell me what kind of bond I mean when I say that? Sigma bond. So if that's the case, what kind of bonds are we looking to move? Double bonds or pi bonds? What's another source of those electrons that we can move? Lone pairs. Where do you start? How do you know where to start a molecule or a resonance structure? Charge is a good place to start. You need some kind of electron source. And you are then going to push those electrons all the way around the molecule as far as you can, or as many times as you can. Yes, following. So sometimes it means moving negative charges. Sometimes you'll see positive charges moving. But what's an important detail of our curly arrows? Yes, curly arrows are showing electron movement. So we never want to start an arrow on an atom. So like, you wouldn't start your arrow here. You would start it at a source of electrons, like the lone pair indicated with this formal charge. And then, because we are only moving those pi electrons, we can't touch this one, but we can touch one of these. And that lands on the atom because now that atom is the owner of the lone pair of electrons. One thing with resonance forms to remember, or a way to kind of like check your work, is conservation of charge. If you start with a neutral molecule, all of your resonance structures should also be neutral molecules. That doesn't necessarily mean that they could have no charge, but it means that you should have a positive and a negative, or two positives and two negatives. Yeah.
This like kind of has to do with this, but it was a question.
Homework 5?
Yes.
Okay.
There's one that has a nitrogen that's like double bonded and then it has two bonds, but it has a positive charge. And I didn't like, since it's full, like surrounded, I just didn't understand why or how the positive would like move.
So positive charges, that means you are going to fill, like a positive charge means that there's like an empty orbital that could take electrons but doesn't currently.
So why, how would there be an empty orbital for bonded response?
Because nitrogen has 5 valence electrons. So that would only be 4 electrons.
One electron, not one pair.
Yes.
Okay.
It's all like carbon likes to have 4 electrons. That's why it likes to have 4 bonds normally. So in this one, we have 1, 2, 3, 4, 5. So it has a negative charge because it has 1 more electron than it needs.
Why do that? Oh, because you're sharing one electron.
So when we're doing octet rule, we can count both electrons. But when we're looking at formal charge, each bond counts as 1. Do we feel better on resonance now? Okay. Resonance is one of those things that really just takes practice. And that's why there are so many resonance questions on your homeworks and stuff. Because that is one of those things that just, the more you do it, the more you will understand it. And because this exam review is happening so far in advance of the exam, you have plenty of time to do practice questions with resonance, should you choose to. Can I move on? We feel good about resonance? We feel better about resonance? Do you have questions? Okay. Do we feel good about this question? Or do you have questions about SN1? Yeah.
In order to get rid of like a positive, like, because with a negative, you can get rid of it by adding hydrogen, right?
Mm-hmm.
So in order to get rid of a positive, like, that really be like hydrogen is attached to it, or, like, I'm just kind of confused.
So we, quench is maybe the word to use here, with a nucleophile. So that's what we have coming in, is the sulfur has additional electrons that it can then share with the carbon. The negative and the positive go together. And so an easy answer for when we have a negative charge is protons, because they're always H+. With cations, you'll see like a base or a nucleophile, something that has electrons to add to the mix.
And so when you're looking at that in a resonance point,
Mhm.
like, because the electrons can go from the carbon to this, to the bond, to the carbon to the bond.
Mhm.
But with the proton, extra proton, it can move between carbons and to the, like, I was just, I don't know,
So with negative charges, those are talking about electrons, and bonds are made up of electrons. And so that's why we can move like from a bond with a negative charge. But a positive charge is a lack of electrons. And you wouldn't see that in a bond, you would see it in a specific atom.
so if there's only two single bonds on a carbon.
So with this, for our octet rule, we would assume there's 2 lone pairs here. And that would put us at 6. So this would have a charge of -2.
And then in the resonance structure though, like just first on the blue one.
Yeah.
Two single bonds, and I get it's because you broke off the ground. And proton in there, but in the second one, like, I'm just like, how did you get the proton?
Well, so the electrons that made this double bond, that I'm moving this double bond, the electrons that were here are now here, which means that this carbon lost this specific electron from its valence shell. So it lost the electron and has an empty space where that electron once was. And that's what's indicated with a cation or a positive charge.
Sorry, I feel like I'm asking so much. But then if you look at it like the way.
Mhm.
Why wouldn't that be negative? If it lost more electrons,
Well, it had 4 in its valence shell, right? Because we had 1, 2, 3, and an implied hydrogen for 4. So here we have 1, 2, that implied hydrogen is still there. 3. We don't have a 4th one.
okay, that makes sense. Thank you.
Do we feel, yeah.
Is this going to be the answer for that question, or can you choose the arrows or just connection?
With this one, you should do the curly arrows. So if it just says your mechanism is curly arrow. Disconnection analysis will be explicitly stated as disconnection analysis, and usually curly arrow method or curly arrow mechanism will mean like
And so we have to draw two arrows at the same time. for it to work.
yeah. What two arrows?
The sulfur compaction
But that's just one arrow.
and moving the double.
Yes, so yeah. Because you have the like, you're making the resin structures and then you're doing the actual substitution. What's your question?
So on the exam, is he gonna want us to do like how it brings it down and then back fix it? And puts the arrow back up to the. Not just like drawing curly arrows on this one, we don't have to recall.
So with SN1 and some other reactions, you will have an intermediate that you have to draw. When you don't have an intermediate, like with SN2 or E2, it would be fine to just draw the arrows on there. But if it's a stepwise reaction where you have a stable intermediate, you need to draw that separately instead of drawing all the arrows on one. What's up?
So.
No. You would draw everything above this line. Yes, so below is disconnection analysis, with which if you're asked to do that, it will explicitly say like, do the disconnection analysis for this. But if it, like this question specifically states, just asks for mechanism, you would do the curly arrows. Other questions? SN1 is stepwise and SN2 is concerted. So concerted means that it all happens in one go. So I'll pick out a different color here. So in SN2, you would have like direct attack of your nucleophile and the kicking off of the leaving group all in one go. Yeah. Yes, because we're showing electrons moving. And so you want to point to where they land. Well, so you have to start from a source. So this negative charge here is the source I'm pulling from in this arrow. And then this bond is the source of the second arrow. I have uploaded a like crash course document that has all the mechanisms. And in that is a detailed numbering of the steps. So you can see what the first step is and why that is. Other questions? Yeah. Yes. I think that he normally will like specify. So it will say explicitly curly arrow. Yes. Sorry, the colors are not great on the projector. Yeah.
The mechanism with like the purity and the image, because that's what was on the board, nitrogen, the lone pair that has to move to, not just the bonds. Resonance structures.
Homework 5. He will cover homework 5 tomorrow. If it's still not clear to you, you can email me and I'll do a video on it. But he doesn't like to really discuss the homeworks before they're due. Other questions? Yeah.
So is this not lecture?
It will just be referred to as SN1.
Okay.
It's the like long name is nucleophilic substitution. That's what the SN stands for, or substitution nucleophile. Other questions? Moving on. So, identify the following reactions as oxidation, reduction, or neither. Provide a clear justification for your answer. So by justification, he means that like bookkeeping method where you show either the loss or gain of electrons. This one does not use curly arrow because it's like a bookkeeping and not really a true mechanism. So, does anyone know where we can start with this kind of question? Yes. Well, that is our main goal. And the double bond is what we see changes, right? So we have double bond here. Let me use a better color. Oh. We have a double bond here that is not there in the product. So first thing we're gonna do is a curly arrow. So I was kind of lying, but we have a negative here, and because we have now taken electrons from that top one, we have both a negative and a positive. So you might notice in our final product that there are more protons. Those protons need electrons to hold on to. So we need to add 2 electrons. Now we have 2 negative charges, so we can add our 2 protons and get to our product. So, is this an oxidation or reduction? Why? Because you gain electrons. Reduction. Are we all familiar with the mnemonic device for oxidation and reduction? Oil rig or Leo goes grr? No, nobody knows the Leo one. That's okay. So you have oil rig. This is the one I learned. Oxidation is losing. Reduction is gaining. Lose electron. Oxidation. Gain. Yeah. I like oil rig better, but other people have learned Leo goes grr. But they both mean the same thing, which oxidation is losing, reduction is gaining. Oil rig should be easy because we're in Texas. I appreciate the pity laughs, thank you. So, next one. Where do I start? What about the double bond? So. I would not draw it like that. I would start kind of in the reverse of what we did here, which is that these two protons are gone. So you can say minus 2H. Now, if I were to push our electrons, I'm going to end up with too many. So what I need to do is lose 2 electrons. That way, instead of ending up with these incorrect arrows that would give me an O minus 2, this gets us to where we need. What kind of reaction is this? Oxidation. Yes. So if we did our like curly arrows right away, we would end up with an oxygen that had a -2 charge. That's way too many electrons and doesn't get us to the product we know we're going to make. So if we take away 2 electrons, then we have that negative and the positive, and it evens each other out. Yes, what's up? You could take the other 2. You would, so if we took the other 2, we would end up with the same thing, just kind of in a different order. You have to take away the 2H. They aren't in your product. What went wrong with what? Yeah, well, so we could go that way and end up with this intermediate, which is breaking the octet rule. And then take 2 electrons from it and end up at the same thing. Yeah. Because we took 2 electrons from it. So if we had taken 1, it would have been neutral. So we take 2 and that's negative. Would it help if I drew the lone pairs in? Okay. Yes.
Check your work by just counting the number of protons. Like going from here to here, there's more protons. More. Oh, this definitely is not sufficient.
That might not always work. Yeah.
So the 2 electrons that are leaving are on the same oxygen. One is attached to hydrogen, and the other one just goes.
None of them are attached to hydrogen because we already got rid of the hydrogen.
So the hydrogen just leaves as H plus first.
Yes, so that's this step. Is we lose the 2H plus.
One pair goes.
Yes. Do we agree with this one? Do we have more questions?
So you said that you would take yours.
Yes. Am I good to move on? Okay. So with this one, what's happening here? Is that an oxidation or a reduction? No. So it's neither. Questions on this one? Comments, concerns? No. If you wanted to, you could do like the mechanism. Good for the next question. So curly arrows for electrophilic aromatic substitution. Where do I start? That is not where I start with electrophilic aromatic substitution. We're going to start with adding our electrophile. And now the key part about electrophilic aromatic substitution rather than electrophilic addition to an alkene is we will lose anyway. I can't wait to tell him that that happened. Oh, he's gonna laugh. Anyway. Okay. Anyway. Instead of having something come add to the cation, because right now we have a negative and a positive. Your first instinct might be, like a magnet, those can go together. That is not what we will see happen here, because aromaticity is super, super important. It makes molecules stable. They want to be stable. So instead of having that bromine add to this spot, it's gonna deprotonate. So it's gonna take the proton so that the electrons can reform that double bond and we can re-aromatize. Questions on this? It is going to the proton because it's forming a bond with the proton. What's up? Mhm. The positive is just on this carbon. When we took away that double bond, we took away an electron from that carbon. HBr is a strong acid and exists in its ionic forms as well as its bonded forms. No, it either would be fine. Other questions on this one? Moving on. So with this one, you have the starting material and the product. What reaction is this? Addition? Any particular kind that we know about for alkenes? I'm hearing whispers of the correct word. Electrophilic addition. Cool. What about the next one? Because you've only learned electrophilic addition. Yeah. And if you want to get real specific, alkene. Yeah. So, what about this next one? What's going on there? Yes. Indicated by this right here. Nucleophilic substitution. It could, we just haven't learned that yet. So for you, it can't. N, negative nucleophilic. Okay, what about this next one? What's our first red flag? That wouldn't be my first red flag, but it is a correct red flag. Addition. Question mark? Electrophilic is a great word to have in this reaction title. Now, I got a question for my friend who said addition. I'm gonna use this one. Where did this proton go in the final structure? Sort of, maybe, we don't know, but it's gone. So did we really add, or perhaps we traded spaces? Substitution. We are missing a middle word. Aromatic. Because our benzene ring is aromatic. What's up?
Wait, so how do you know if it's addition versus substitution?
Well, addition, we'll see something added to both sides of the double bond. A substitution, we'll see like two things basically trading spots. Yeah.
If it's has an aromatic molecule in it and its substitution, will it be aromatic substitution?
If the substitution is happening on the aromatic thing, yes.
And will he ask us something like that?
Like what?
Like that tricks us kind of like that?
I would not call this a trick.
Okay.
This is an example of electrophilic aromatic substitution. You have an aromatic thing that got stuff added, substituted on it. Yeah,
Explain aromaticity.
I have a question about that. So if you are patient, we'll cover it.
It's on the right side of the reaction, that just showing like the resonance force.
Yes,
How do we know it's aromatic?
we'll have a whole question about that. The short answer is it a conjugated system of pi electrons that follows the rule 4n+2? Okay. Oh, yes, double questions. Electrophilic is a cation, so something positively charged. Nucleophilic is negatively charged. Yeah. Oh, that's me indicating that I was going to talk about this example and not because this proton. Other questions? Yeah.
So for the hydrogen, does it matter like which hydrogen is taken off?
Which?
For the substitution, so you know how you drew that hydrogen that goes away for the substitution?
Yeah.
Is it just like any hydrogen? Like not any, but one that makes sense for substitution?
Yes. So that's why you see two products with this one. Is because you could also take off one of those ones. Other questions? Okay, what's our oh, yes. Because we are substituting our proton for a new thing, not just adding to the molecule. Because we also, like, if we were just adding, that proton would still be there, but it's not. And so it has been substituted out. Yes.
And since this is not, that's another thing.
Yes. Other questions? Okay, what's my last reaction? Oxidation. How do you know? Yep. So with oxidation and reduction, it might be helpful or faster to just know the biologically relevant oxidations and reductions that we see. So it's like alcohol to aldehyde to carboxylic acid, or alcohol to ketone. And then you have alkane to alkene to alkyne. Who knows what an alkyne is? Yeah, okay. Just wanted to make sure. There were like some blank faces after that. I said that, so, but you're right, alkyne is, so you have, alkane is CC, alkene is a double bond. Alkyne. Bond. Yeah.
I know I answered the question, but how does it? It breaks off. It just has it. Oh, yeah. Why does it make it down?
Because we took a proton from there. Don't let the implied hydrogens get you. Drawing them out is helpful for lots of things, especially NMR, because NMR is looking at protons. Okay, how do we feel about identifying reactions based on like starting material and product? Okay, I have some other practice problems about it later. We'll do those first. Okay. So this is looking at kind of the same concept. Oh, wait. Okay, don't do this one. Not there yet. But yes, you can do all the other ones. So, reaction 2. What's going on here? Yeah. Yeah. What is that called? Acid-base reaction. How can we identify an acid-base reaction? What is happening? What should we be looking for in the reaction? A proton moving. So we had a proton here that we then lost because it landed on the base. If all that's changing is one proton moving, that is just an acid-base reaction. You have your acid. In this case, you had an explicit base. You then have your conjugate base and your conjugate acid. Yes, no, maybe so. How do we feel about it? Okay, next reaction. We go from this molecule to this molecule. What happens? What kind? Why? Yep. Oh. What about reaction 4? There's like a major. Yeah. How do you know? It's losing those electrons. So we're going from single bond here to a double bond here. What's next? What changes? Addition. Do we know if it's electrophilic or nucleophilic? not a great response, but yes, we don't know with this one. So it's addition to an alkene. And what about this last one? Oh. What kind of thing? Mhm. And are we just adding or are we substituting? How do we feel about a question like this? The proton that was here is now not here.
That's why it's a substitution.
Yes. What's up?
I'm sorry, I know we have lots of oxidation reactions.
Yeah.
We lost two electrons. Why do we have them?
That in losing the 2 electrons, we formed a double bond. So we can draw out the like steps to that. Two negatives will not react with each other. So we have to lose 2 electrons. Then we have a negative and a positive. Those can react and form our double bond. What's up?
Oxidation reaction, what are things for which the double bond forms, or is that just-
So one example of oxidation is aldehyde to carboxylic acid. That is not forming a new double bond. So no, not always. Yeah. It could be either. Both are nucleophiles that are substituting like each other. Other questions? Thumbs up, medium down about identifying stuff using the starting material and product. Okay, mostly middles and ups. At least it's not mostly downs. Okay. I'm gonna do aromaticity next. So there's like a flow chart that we can follow when approaching the question of aromaticity. And the first question is it a conjugated system? Can anyone tell me what I mean when I say that? Pi electrons. So we're looking for pi electrons that are all talking to each other. that make basically a ring. So it doesn't have to be the entire molecule, but there needs to be some sort of complete ring for the electrons to have like kind of perpetual movement. So I know there was a question on one of the homework questions where the dead center carbon of 3 rings together did not have any pi electrons. So how was that still eligible to be aromatic? But it's because on the outside of all the rings, you have that unbroken system. So after we answer the question of yes or no, if there is no conjugated system, that's not aromatic or non-aromatic. If there is a conjugated system, we have another question to ask. And that is using this equation 4n plus 2. And we set that equal to the number of pi electrons. From that equation, n will either equal a half number or n will equal a whole number. If it equals a half number, that is where we get anti-aromatic. If it equals a whole number, we have found an aromatic compound. They are different. So I think Dr. Begley mentioned this in his slides, but anti-aromatic compounds are very reactive, whereas aromatic compounds are quite stable. Yeah, like the homeworks. So let's get started with this. What do we think about that first one? Where do we start? Is it a conjugated system? Too tiny. But yes, that little square in the middle is a conjugated system. So we can now move to 4n plus 2 equals the number of pi electrons. How many pi electrons are in our little conjugated system here? How do you know that? Yeah, so we have 1, 2, 3, 4. We do some algebra. So what is this classified as? Anti. Yeah. Mm-hmm. Mm-hmm. Yeah. Because they aren't participating in our conjugated system. No. Only that center ring has a conjugated system. Yeah. Double bonds are not the only way to have a conjugated system, but a good like rule of thumb for a conjugated system is like every other bond is a double bond. Now, that's not the only way to have a conjugated system, as we'll see with this question. I'm still answering questions about the first one. But yes, the one below it is the one where, yes, that has pi electrons that aren't in a double bond. Yeah. You mean like something like this? This would not be a conjugated system because this carbon here does not have any pi electrons. This also chemically wouldn't happen because once you add double and triple bonds, things linearize. So like that's why we see our alkynes drawn like that sometimes. So to put two double bonds next to each other in a ring would never happen. How do we feel about the next one? Anyone feel confident about their answer? And want to come up to the board, up to the iPad? Come on up. Yeah. Although you could really do any of them, and I would be okay with it. Let's just do the next one. Ooh. Can you justify your answer?
Well, and like which way? Can I just like
math
say
way.
the two? Oh, okay.
Does everyone agree? Can I get thumbs up or down? Good. I hope you all agree because it's right. And this is anti-aromatic. What about our next one? Any brave souls willing to work this one out? Come on up. Also, are you counting all your pi electrons? Counting all the pi bonds, but don't forget, lone pairs are also pi electrons. If you use the back arrow. Everyone agree, thumbs up, down, middle? I hope you all agree because it is correct.
Yes.
There was a less enthusiastic, yeah. So 2, 4, 6, 8, 10, 12, 14. Yep. What's up? Because every carbon in this, every atom in this has some pi electrons. Or the capacity to have pi electrons, as we would see with like a positive charge.
It doesn't.
Okay, what's up? It'd be like one hydrogen. So it would have an implied one. And then a lone pair. Other questions on this one? Okay. Moving to the next one. How do we feel about this one? Is it worth me going through all of these? Yes. Oh, okay. I don't know, I feel like I was losing the room a little bit. Who wants to come do this one? I'd also like you guys to know that the right answer is up on my computer. So if you come up here and you're like,
wait, do I? Oh,
do your math. Yeah.
So it's 4. How do
I don't know if you have much room there. You can just,
well,
yeah.
2, 4, 6, 8, yeah, 12. So then it's like something.
You put 10/4,
Yeah.
or you could put 5 halves.
4. Yeah, there we go. So it's anti-aromatic. But I can't write. I spell that right? I think I did. Anyways, there you go.
I'm glad your tests are more legible than this. Okay, do we all agree? Thumbs up, middle down. Great. What about this one? Yeah? Would it be, do we want to just have the right answer? I would like to be mindful of your time. And so if we can go through these faster, but also it's good practice to work them out up here. What? Yeah. Well, what answers did people get? I heard the right answer overwhelmingly. You have a lone pair here. The nitrogen has a lone pair, therefore has pi electrons. So it's a conjugated system. What's up? It's included. The amine is included and its lone pair is included. Yeah. That's more than you bargained for. Just count your electrons. Okay, what's the answer for the next one? Aromatic. Oh, I got it. Cool. What about the next one? And bonus question, what's this molecule called? Benzene. So true, guys. What about the next one? Neither. Why? Not conjugated. We've got 2 spots that don't have pi electrons. What about the next one? I'm hearing two answers overwhelmingly. Okay, that's one of the answers I'm hearing. What's the other one? For someone who said neither, why did you say neither? For someone who said aromatic, why did you say aromatic? Where did all the people who said aromatic go? I'll give you a spoiler, they're right. This ring is aromatic. Because you have pi electrons on, I'll do it in a different color. These two carbons have pi electrons from being in a double bond. And this cation has an empty orbital for pi electrons to move through, making it a conjugated system. Because we could draw a resonance form like this. Blah, 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 rest of the ring. So this one is aromatic. What? They don't have pi bonds. That's what makes the bigger ring not aromatic. The bigger ring does not have a conjugated system, but the little ring does have a conjugated system. Yeah.
So just because the little ring is aromatic, does like make itself a big one?
Aromaticity is powerful. Yeah. Just your answer. Other questions? Yeah. If the positive were a negative. I think your question will be answered in the next three. Because the difference between the next three is no charge, positive charge, negative charge. So, what's the answer to my next molecule? Neither. Yeah. We don't have any kind of conjugated system here. What about the next molecule? So true. What about the next one? So true. So, replacing that cation with an anion, you would increase your number of electrons, and that would change it from aromatic to anti-aromatic. They are redundant. Like the lone pair on a carbon indicates the need for a negative charge, and a negative charge on a carbon should tell you that there's a lone pair there. We don't normally write out our lone pairs. Questions? Yeah. You technically don't have to. We're just looking for the right answer.
So like say that one plus and then plus.
I fear getting into hypothetical, well, what if this changes? Well, what if this changes? We'll lose the point. Your homework are very apt to the test. Have you seen that in your homework somewhere? Okay. Then I'm gonna say we don't talk about it. How do we feel about determining aromaticity now? Lots of thumbs up. Very good. Okay. I have a couple different options, and I'm gonna let y'all pick what we do next. We can do an elimination mechanism, draw a molecule, or NMR. Cool. So, NMR. There is a sequence of steps that you follow with NMR, where once you learn those steps, it is a rinse and repeat every time you see an NMR structure. So the first thing you'll look for is the number of proton groups. This is going to tell you your number of peaks. Then within those proton groups, you'll see how many protons per group. And that will tell you the intensity of your peak. Then you will look at neighboring protons. And that will tell you the splitting of your peak. Key to remember with this step is that it's n+1. Finally, you can use chemical shift. And that tells you where on the x-axis your peak will lie. This is all the steps needed for NMR. So let's break that down. With this first molecule, I would say it is always a good thing to start with your implied hydrogens. Draw them out so that they are easier to see. Now we can go about identifying our proton groups. How many proton groups do you guys see at first glance? I'm hearing a wide variety of answers. So all of these methyl groups are identical. They all see the exact same view of the rest of the molecule. And so they actually make up one single proton group. With benzene rings, if you have symmetry, that will also cause groups to be combined. And in this one, we do have symmetry. So this is our second, this is our third, and this is our fourth. So we expect to see 4 peaks. How many protons are in group A? 9. So we would expect to see an intensity of 9 for this peak. What does intensity mean? When I say that, what are you thinking about with the graph? How tall it is? B is how many? C? D? Exactly. So that's step 1 and step 2. Now we can look at splitting. This is what I would say people struggle with the most when it comes to NMR. So stop me if you have questions. We are going to look for neighboring protons. We can only travel one bond away. Does this carbon have any protons? No. So in our n+1, what is our n? 0. So we would expect that A is a singlet. Looking at B, does this carbon have any neighbors? Or any protons? Does the neighboring carbon have any protons? What if I look at my other neighbor? How many? 1. So B, we would expect a doublet. What about C? Also a doublet. And finally, what about D? Singlet. So the final step is using chemical shift. And this is the table we have for chemical shift. Chemical shift is a lot like pKa, where it is a little bit fluid. It changes based on what else is connected to the molecule. This is your least trustworthy of your steps. That's why we put it at the end. And I prefer to use it as checking my work. So we can actually take our knowledge already and start labeling an NMR. So we have 3 NMRs here. What would you say is your first thing to look for? What is the most striking about this molecule to you? Everyone can have a different answer. Whatever it is, for me, it would be 1 singlet with an intensity of 9. 9 is a lot. So we look here, and lo and behold, there's only 1 NMR that has that. So we can label our A. B and C are aromatic. You will not ever have to identify between these two which one is B and which one is C. You will just put them in the aromatic region. And that leaves us with 1 left, which is D. If we zoom in, we can see these are both doublets, 2 H doublets, which is exactly what we predicted they would be. What's up? Like I said, you won't ever have to identify them, but you are right. It is the chemical shift is based on being close to those heteroatoms. So a higher chemical shift when you're closer to a heteroatom. Yeah. No. I did that in my office hours because I was working with just a whiteboard. You will never have to draw an NMR. So that's 1 out of the way. We then move to our next one. How many proton groups are here? Anyone have any thoughts? You are all too 7. there is not symmetry with this benzene ring. And so these two protons will be unique.
Like at the top, the CH3, but not listed.
Well, this one is 3 away from the oxygen, and this one is 4. One of them is ortho, or no, one is meta and one is para to your ester or ether. Me means methyl, so it's a CH3. So now that we have our number of peaks identified, 2 participants, who else is in here? Oh, me twice. Anyway, we can break down what we assume the intensity to be. So what is our assumed intensity of A? Step 2 of our process. 3. What about B? C? D? E? F? F? G. So now we can look at neighboring. Does A have any neighbors? No. So what peak do we expect it to be? What about B? What about C? A quartet, yes. So we see all 3 of our neighbors here. So C is a quartet. What about D? Triplet. E? F? G? Yep. So now we can look at our NMRs for one that has 7 peaks. I'm pretty sure it's only going to be one of them. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. This one has 6. This one has 7. So now we can go in and identify our peaks. So we have 2 singlets that are each worth 1. And lo and behold, we have 2 singlets that are each worth 1. Now, we have splitting with C and D that help make those clear. Now, we have 3 separate 3H singlets. This is where you want to look at our chemical shifts because those are all kind of identical. And if we look at our chemical shift, we see that a methyl is like 0.85. But off of an oxygen, it's like 3.3. So G will be our more upfield one. And then A and B will be these 2. When it's something that close, you won't have to identify which one is which. Yeah. I am not following your question. Okay. Hmm. Yeah. Yes. So singlets is looking at our neighboring atoms. So with this one, our protons are not really the money makers of neighbors. So we're looking at the carbons as kind of the keepers of protons. So we can explore every direction, but at most one bond away. Neither of these carbons have any protons of their own. So we have no neighbors. And our rule for neighbors is n plus 1. So that's how we get a singlet. But with this one, we look to the right and we have 0 neighbors. We look down and we have 3 neighbors. 3 plus 1 is 4. That's how we get a quartet. Yeah.
This is a little bit off. Very close. But, like, when you're answering these questions, you have to write out, like, I have for each one says single.
No. You just have to label the signals. So the like ABC that I'm doing on the molecule and then on the NMR. So like the base answer for this would be is that right? Yes. And then labeling those on your NMR. So this final molecule, how many proton groups do we have? Seven. How many, or what's the intensity of A? What's the intensity of B? C. D. E. F. G. What kind of splitting would we expect A to have? Yes. Did you have a question? This one is hiding. And I didn't catch it at first. What splitting would we have for B? C? D? E? F? G. So now we can use this information to label our NMR. For A, we're expecting a 3H singlet. We've got 2 options for that right now. For B, we're expecting a doublet. For C, we're also expecting a doublet. For D, we want the 2H quartet. There's no question about this one. It's our only 2H quartet. E, we're looking for a 3H triplet. There's only one, so no question mark there. F is going to be another one in our aromatic region. And G is going to be the other 3H singlet. With these ones, our aromatic region got a little bit messed up, which that's science sometimes. And so we can label all of these as just our aromatics. With these ones, they're too close for us to make a differentiation, so you can just label them both. Do we feel better about NMR now? What's up?
Thanks. Can you give us an example where
No, that's a me making practice problems issue. Other questions on NMR. If you attack it with this same roadmap, you will always get them right. This is like an unfailing system. Yeah. If it's possible to differentiate them, like if it's a methyl versus a methyl attached to an oxygen, that it's possible to differentiate. But if it's two methyl groups, that is not possible to differentiate for you guys. Any other questions on NMR? Okay. I have a elimination reaction and a draw molecule. Which one sounds more appealing? Cool. So I've got an elimination reaction here. Specifically, an E2 reaction. What does it mean that it's E2 instead of E1? In the back? No intermediate. AKA, it's a concerted reaction. Where should my curly arrows start? Yeah? One is nucleophilic substitution, one is elimination, but they are both concerted reactions. That's what the two means. Yeah. What about the hydrogen? How is it going to kick off? With our nucleophile. So I'm going to redraw our nucleophile up here, but it's just the same thing. It is going to take that proton. Those electrons have to go somewhere. And they're going to form a double bond that results in the kicking off of the bromine. And that's it. In a concerted reaction, you don't have any intermediate. It all happens in one go. And if we follow these electrons, we end up with these products. If you were doing a curly arrow mechanism with this, yeah. Yeah. Other questions? How would you approach this question with disconnection analysis? I like that answer. We need a little bit more though. Disconnect the BR. What else can we do? So now we can do H star, R star. What else do I need to do? Yeah, not exactly what I'm looking for though. Because rearranging doesn't mean writing anything new. I'm looking for what else we can write. Indicate what bonds we made. And that is the disconnection analysis method. Yeah. Yeah, I mean, you can just kind of have them in groups. Yeah. It depends. So the question will explicitly ask you to do disconnection or the curly arrow. But for the sake of practice problems, I've just been having us do both. Other questions, comments, concerns? What are the other kinds of elimination? We have E2, E1. What's the other one? Those are nucleophilic substitution. Nope. Close. What is E1CV? Yes, E1 would be with an intermediate. What about E1CV? Anybody? So close. It's catalyzed by a base. But because it's E1, you will still see the formation of an intermediate. But it just means that you are starting with a base. Yeah. So an intermediate means like I would do a big arrow and then draw something like this. I got 2 questions coming at me from 2 different sides at the same time. Someone go first. Yes, so E1 is stepwise. You will have that intermediate. E2 is concerted, so you will do it all in one step. And that's the same premise for SN1 and SN2. Other questions? Comments, concerns? Okay, the last question I have is Draw a molecule. I'm gonna give you guys like 3 minutes, 2 minutes to try it on your own. And then I'll talk you through my thought process when approaching this kind of question. You will not have a pKa table on this one. So you should know your functional groups. No, you don't ever have to memorize your pKa's. But I know that some people last time used the pKa table as a way of getting around memorizing your functional groups. And you will not have a pKa table on this one. And the NMR thing does not tell you your functional groups. Yeah. Yes, there was a slide. I don't know if it's fully updated because I don't remember what's on it. Yes. That is because homework you can use Google. But that would not be on an exam. Other general questions. Yeah. So I set up all of the rubrics as positive grading, where you build up from 0. Sometimes the graders delineate from that and add in a minus, but the base of all the rubrics is built up from 0. Yes. So like you would get a point for having the 6 carbon ring and a point for having the 7 carbon ring and a point for having the benzene ring. You can see the rubrics for the last exam on Gradescope, and it shows that, like, you can use that as a guide for how a question like this would be graded. Yes. Mhm. No. No. You would have something more like this. Yeah. Okay. No. Hey, the homeworks are not graded on correctness. So it's okay if you have realized that you got all the homework wrong. You tried it and you can submit that because you tried your hardest. Yes. So I would approach this one by first drawing out all of the rings. So I have a 5 carbon ring, a 6 carbon ring, a 7 carbon ring, and a benzene ring. Now, I'm just going to go in and add the functional groups. That is a thioether. This is an alkene. That's an alcohol. This is an ester. This is an amine. And this is a ketone. I have a chiral center here. I have a chiral center here. Questions, comments, concerns on a question like this? Yeah. Can you speak up a smidge?
Sorry. For the last exam, did they take off because we're having like too many?
There's no stipulation for too many carbons. There might have been a stipulation on too few because I believe it specifically said 20 carbons. Any other questions, comments, concerns? That's the last practice problem I have for you guys. Yeah, I will have, oh, I don't have any office hours between now and the exam, but Dr. Begley has office hours tomorrow, and I am easily accessible by email. I don't know. That would be a question for the guy who makes the slides. I don't know if I can answer that. Yeah. I would say to study the things that we have gone over today and have been in the most recent homework. Huh? Yes. Any other questions? Yeah. Yeah, it's up to Monday's lecture, I think. Yeah.
What should we focus on when we're looking at the last exams for this exam?
I think that's too specific.
Okay.